thought about this title. How many are part of great marriages? Okay. For me, sometimes. It probably should have said shotgun marriage because, we're still working this out. But in any case, no, don't do that. I was just thinking about that. Okay. So last year I talked about Exascale Computing Project. Really, the results were just starting to come out on Frontier. And so this year, with Lori Dyson's permission, she's now the director of ECP. I'm going to talk a fair amount about kind of the projects crossing the finish lines, and took Hong here as a key sponsor. So I am going to spend a fair amount of time kind of reflecting back on what was done, what we learned, and then conclude with some remarks on AI. When you add up the total number of GPUs on these systems, and it's somewhere north of 100,000, it's a pretty impressive number. But I read the press release from Meta where they have at least 650,000, and some people are saying maybe 1 million. And so this is an impressive resource, as we'll show. But we're certainly not the big kid on the block, okay? But I think what it does say is GPUs are here and they're important, and we need to exploit them as much as we can. And so Frontier is operational, Aurora is being delivered and will soon be operational, and El Cap is coming, and they're great systems. They really are. I think we're really finding out just in the case of Frontier. I moved from Overidge about 6 months ago, but I stay obviously in close contact with my colleagues there. It's really becoming a very stable system. Oops. So again, the Exascale Computing Project, we're fortunate to have the Department of Energy sponsorship. Tuk Hong is one of our key sponsors. Most of the DOE lab system have been involved, and it's a kind of a first of a kind, a large software project moving in parallel with hardware procurement and deployment. What a novel concept. That's a great thing, at least in my opinion. So I'll overview a little bit and then dive down into some examples. So the key leadership listed here, not surprisingly for a large software project like this, you need to deliver applications of importance to DOE mission space. So those applications were carefully selected about 7-8 years ago, and really are just the first mover applications, when in fact in the U.S. Department of Energy, there are hundreds of applications that are regularly exercised. And so these first movers were strategically selected in concert with the various program offices about the Department of Energy. Andrew Siegel and Eric Drager have led that effort for many years. Mike Carew at Sandia, Lois Kerf-McGinnis at Argonne, leading the software stack. And again, I'll say a little bit more about the stack later, but relative to past procurements in 10, 20 years ago, this effort really wasn't embedded in lightweight kernels of the operating system, et cetera. So the software stack really sits above the operating system. Previous speakers talked about a lot of the software, at least some of the relevant software projects like scheduling, et cetera. And then make sure that the software is deployed and operating, in a stable way with CI/CD, et cetera, on the hardware, led by Richard Gerber and Susan Coughlin. So again, this is kind of a pretty eye chart of the application portfolio. I won't have time to go through all of them. There are a number of podcasts, articles being published that you can find at exascaleproject.org. Again, each one of these points to one or more DOE mission programs in scientific discovery, fundamental science, applied energy, and national security. And so a lot of them sit within the Office of Science, which is a 6-program office that's about, I'll look at Tuk, I'm not sure, $8-9 billion a year. So it's a reasonable investment here. So the application projects really, each project, not surprisingly, tends to have one or more kind of multiple, one or more single physics or multi-physics codes. In this case, the 24 application projects really represented about 60-plus separate codes. And that doesn't mean the codes aren't interoperating and talking back and forth and working in concert in parallel on nonlinearly converged consistent solutions. Often the codes are running on different parts of the machines, doing their thing and talking back and forth. So really trying to orchestrate multiple codes on a given system. Each code has its own unique footprint in terms of hardware and software. So definitely a heavy lift. I don't think I need to convince this community. So the application projects are really on the hook for key performance parameters, about half of them, 11 of them are on the hook for showing new capabilities as well as increasing performance. And then the remainder were more kind of first mover applications. So they were on the hook for showing that they could address certain physics and chemistry type problems, and not directly on the hook for performance. But basically, the performance target was 50x, and it wasn't 50x faster answer or 50x more science. It was kind of a combination of the two. So 50x was a science work rate. So think of like a Monte Carlo code. Particles per second is a reasonable measure of science. And so each application had a rate that it needed to, or at least of the 11, that it had a rate that it needed to show 50x or more improvement. The kind of the minimum for the project to be called a success was 50% on both sides. And so it's really, really satisfying to see that most of the applications will meet their metrics, which is something we really didn't think would happen, because these metrics weren't easy. Here's some examples of, and apologies for all the acronyms here, but some examples of the application performance. And basically the 70x was relative to a baseline simulation done in 2016. So that was like Titan at Oak Ridge and Theta at Argonne. In other words, the canonical kind of peak speed at that time was sort of 20 petaflops. So hence the 50 to get to 1,000. When we all know that performance of these codes doesn't directly scale with peak flops. It scales typically more with, say, memory bandwidth. But in any case, it looks like EQSIM was really sandbagging, but in retrospect, discoveries happen. Gee whiz moments happen. You put enough resources on a team at working on one problem, and great things happen. You can't plan these discoveries or these innovations, but they do happen. And each application has a kind of a key program sponsor. This is Mike Caru's slide. He sort of talks about 100x, but you can see a little bit more detail in terms of the specific challenge problem. I didn't mention that. So each application had to sign up for a very specific simulation that they couldn't do at the time. And it might be typically as more physics, often more resolution, whether it's temporal or spatial, more particles, etc. And so that was sort of spec'd out in 7-8 years in advance, which is hard to do when you don't know the systems. But in any case, the other requirement was, in this case, Frontier system has about 9,400 nodes, and so they needed to run on at least kind of 3/4 of the system. So in other words, you use the capability in a scalable way, but also you can't cheat and not use the GPUs, when in fact that's not surprising, because about 96% of the flops are in the GPUs and all the memory bandwidth you care about. So, as opposed to, and I think the previous speaker mentioned this, apologies, as opposed to maybe 7-8 years ago when I think it was me and Bob that mentioned this, or maybe Jim. Anyway, most of the applications now just live on the GPUs. They're GPU resident. And I know it was Dan Stanzione. Yes, a lot of the compute cores are really idle, not doing a lot, because the game now is fit into the high bandwidth memory work on the GPUs. So most of these codes are GPU resident from the start. There might be some compute cores doing orchestration and some of the networking, but for the most part, all the action's down the GPUs. So if we talk about key ingredients for the application porting, and this is an eye chart of the new science, and I'm not going to have time to go into each one of these, but there are some very non-traditional applications that have really crossed the finish line. Two are listed here. One is a power grid. That involves everything from mixed integer programming to differential algebraic equations, scalable nonlinear optimization, not a traditional HPC application. Exabiome is metagenomics. So there you're talking about a lot of hash tables, a lot of sorting. Kathy Yolich has led that effort, done a fantastic job. Here you have climate modeling. This was the first climate Gordon Bell winner last November with what the application called Scream, basically doing kind of 1 kilometer level resolution in the atmosphere, at least regional, more like 10 global with a subgrid model for cloud mixing, computational chemistry. And this one's way cool in that it's molecular dynamics for metal alloys, but now you're firing off, say, 100 different simulations, filling up the Exascale computer, doing replica dynamics. And if the statistics are right, you can essentially do a large time step jump that's the sum of the individual time steps for each application. And so that one's really an ensemble-based approach based on lamps. Again, some more applications. Computational cosmology, Salmon Abib at Argonne, probably the leader in the field here, not surprisingly, has done some fantastic things. This one was another unique application where basically we wanted to really try to tackle, and I would say we made some headway here, being able to process data that comes off large Department of Energy facilities. In this case, a light source at SLAC is known as the LCLS2. So XFL for free electron laser is really processing the data locally. About a quarter of the data is thrown away, another quarter can be processed, another half thrown back to the mothership. Ian may have talked a little bit about this yesterday with regard to APS. In other words, a good sort of exemplar for using Exascale for processing data on our large facilities and trying to get more out of our data. Another computational chemistry, computational fusion. In this case, a tokamak geometry led out of Princeton, coupling a core plasma physics, more kinetic-based code with a continuum-based code at the edge. Basically, to simulate an entire fusion reactor requires multiple codes, and these are just two, probably another 4 or 5 when you look at the blanket and the plasma-facing materials. So again, some applications here that are not surprising, some that are non-traditional. Particle-based simulations, quantum Monte Carlo, nuclear reactors, in this case for neutronics. So you see a common theme with particles. Another, QMC package shown above there. Combustion simulation, and believe it or not, we still have internal combustion engines. They're here for a long time, and in particular now focused on land-based turbines for gas power plants. Subsurface simulator, really trying to couple geochemical cracking around well bores as well as long-term carbon capture reservoir stability. So just a whole slew of applications. And in terms of AI, the only one that was really kind of had card-carrying machine learning at the apex of the pyramid was CANDLE. That's Cancer Distributed Learning Environment. Most of the applications did integrate machine learning at some level, whether it's for a subgrid model, orchestrating the simulations, et cetera. But only one really kind of had machine learning as the application. That may change moving forward. I'll say a little bit more about that. Again, some other applications. Another kind of non-traditional one that I really like is ExaWind. In this case, not just simulating one wind turbine and its interaction with the background environment, in this case, local weather, topology, but trying to simulate a whole wind farm of, say, 30 to 50 turbines. We're not there yet, even in Exascale, but in this case, wind farms often don't do well in extracting a large fraction of the potential energy because of turbine-to-turbine interaction. So that was the focus for that one. So you can see we had a lot of science focus really driving it. So the kind of the main sort of metric for this whole project is, do we have applications addressing real challenge problems for the nation in this case, or in many cases for international problems? So as this community realizes, it's not just porting code. You really need to rethink, in many cases, your algorithm wholesale. In the case of the Monte Carlo codes, you have one big sort of do loop, so to speak, looping over particles, and that had to be totally rewritten, broken down into different kernels, moving from history-based statistics to event-based statistics. So I think it's mentioned here in this slide. Really a lot of rethinking, reducing the branching so you can get good kernels that stay in the GPU. You can stay GPU residents. Not surprisingly, it's not easy to strong scale in a GPU. You got to keep feeding the beast. So a lot of batch sparse linear solvers and a lot of interesting work in linear solver space that I think is kind of scratching the surface. Also, the project did devote a fair amount of time the last few years into mixed precision. In other words, we may want to keep 64-bit precision, but can we utilize the low precision hardware? And there's some interesting results that came out of that. And looking at kind of where we started to where things are now with regard to the programming models, this project did not really mandate a particular approach. We did not mandate don't use Fortran or only use OpenMP. Essentially, the project supported a number of different programming models. And what we saw with the project teams is they tended to migrate to certain areas. In this case, migrating to some extent away from Fortran and maybe in more of a surgical fashion. About half the codes were really Fortran-based in 2016. And so when I say surgical, not necessarily wholesale rewrite, although one code, NWKen EX, did go wholesale rewrite. Most of the codes that were Fortran were more surgical in their movement. And the programming models, native GPU here say I'm going to write in CUDA or HIP myself, okay? I'm not going to have an abstraction layer. Loop Pragma's OpenMP, OpenACC as an example. Cocos, Raja, and I have a few slides on Cocos because I think there's been a real success story. And Raja is a similar capability at Livermore. Cocos originated at Sandia. And then co-design libraries, which I think really did succeeded more than we expected. There's some papers given there. So again, holistic rethinking, restructuring was required. So this is certainly a contact sport. Co-design on the software loop and leverage a lot of other tools. In this case, with complicated architectures, heterogeneous architectures, most of the application developers really needed to, and I think, learn to rely on other teams, and that's not easy. I'm an application developer myself, and you really want to be able to control your software stack. In this case, being able to leverage other efforts and utilize them, exploit them, and also make sure they stay around is important. So again, it's not optional anymore in our view. We really have to exploit these architectures. Off the shelf is rarely sufficient, and having multiple competing implementations is ideal. In this case, I can think of several applications that really were able to utilize multiple solvers, say sparse linear solvers, and with the CIC infrastructure to do that, now you can compete the solvers against one another. We found that our solver groups really did kind of go after it long and hard when given application said, well, I'm switching to another approach. And so that really led to sort of this, I guess I'll call it one-upmanship and internal competition between the project PIs. And so that really did, I think, help us all in the end. So in terms of integration, I'll say a little bit more about, so we had this, as part of the project, building a software stack, which we named, Mike Carew named E4S, Extreme Scale Scientific Software Stack. The applications did bring in through the stack a lot of these different kind of base capabilities. I mentioned extractions, and I'll say a little bit more about that. But viz and analysis, numerical infrastructure, build deployment. I mean, the SPAC capability from Todd Gamlin out of Livermore really changed the game in terms of our ability to build and deploy. So this sort of list of software capabilities, again, that for the most part are kind of decoupled from the applications, is probably not a surprising list, but that's essentially kind of represents the kind of 100 component software stack that's out there. Just to give you a small sampling of the integration examples, I mentioned the wind farm really drove sparse linear solvers. In this case, basically preconditioners for both Hyper and Trilinos, multi-grid preconditioners in both Hyper and Trilinos. QMC Pack was really able to overcome a lot of barriers with batch to dense linear algebra. So think sort of small matrices, each living on one GPU, and many matrices being farmed out at once. Power grid optimization, again, indefinite solvers for optimization. XSMR, in this case, really overhauled the Monte Carlo algorithm to be more event-based statistics. AMR was really crucial in the accelerator effort, and I'll say a little bit more about that. And non-uniform FFTs really became a real game changer for the Exascale project. And surprisingly, we all use FFTs, and most of us are, making 3D FFTs out of 1D FFTs, and they're mostly uniform. And so non-uniform FFTs was a real gap area for us. So a great example of what we call a co-design center, and everything was kind of co-design in ECP, maybe not so much at the hardware level, but up and down the software stack. AMRX, which comes out of Berkeley, which is Adaptive Mesh Refinement at Exascale, basically is patch-based structure mesh refinement, but that's kind of one key motif. But, once you have that, you buy into that motif, you have to tell yourself, how am I going to push particles on that motif? How am I going to solve how am I going to do linear solvers? How do I do boundaries? And so AMRX really had kind of 4 or 5 key technologies, and you can see all the codes that eventually adopted AMRX, and then the software integrations, solvers, and as well as other build capabilities, in this case SPAC. So AMRX is, I think, a real shining star that came out of this project, really being kind of an underpinning to a lot of the capabilities, and it's open source. And in talking to ISP vendors out there, I think a number of them are going to be adopting this capability as well. So that's a real that's an example of an application kind of living on top of a pretty dense vertical software stack, and the application itself is a pretty thin element on top, basically solving the physics equations. And another co-design center, as we call it, was something known as SEED. So this is going after another motif with unstructured mesh, finite element discretization, and comes out of Livermore. And a lot of our unstructured mesh codes eventually adopted SEED, and SEED is a key library called libmesh. Adopted SEED as essentially the fundamental infrastructure for gather, scatter, finite element discretization. The XASMR project, in this case, used it for the stratified fluid flow within the reactor. And so a really nice example there. I mentioned the XON project. Let me just say that basically what the XON project found is really was suffering from strong scaling, and went to our solver teams, and the result was some interesting algorithmic improvements in GMRes, basically trying to improve, in this case, the strong scaling due to kind of cheating a little bit on the global reductions. And this approach has since been adopted by a number of other projects. So reasonably good performance. This project really drove the Hyper team and the Trilinos team to go after better on-node implementations of Krylov solvers. This is the part in ECP. The Streamkill software stack is made up of SDK, software development kits. The SDK kit is a linear and nonlinear solvers themselves, and what's shown here is all the products. I'm sorry, over here on the top, all the solver libraries as part of XSDK, and then all the consumers of those libraries. And so the solver libraries actually used kind of each other. So there are some interdependencies there, but you can see how for a lot of the products coming out of ECP, there's a lot of solver use. So there's a lot of sort of inter XDK operations and dependencies, as well as outside of XDK. So this is just one of the kind of 6 software development kits in the overall software stack. I mentioned multi-precision at the beginning, and then this is really pushed by Hartward Angst and Jack Donguera, and basically we supported efforts where underneath the covers of an application asked for a solver solution at 64-bit. If there was mixed precision hardware, the library would pretty much automatically try to do that mixed precision hardware. In this case, you do the residual calculation in higher precision, and then you do the preconditioning in lower, and you kind of basically iterate back and forth to get a 64-bit solution. And so a lot of the mixed precision work has gone on here and is inside these various libraries. SLATE is kind of the overall acronym for a lot of the libraries that sit within SLATE. And, these are things that basically replace things like LAPAC, et cetera, BLAS. And so I'm not going to get into the details here other than just to say that to return a 64-bit precision result, often you got 2 to 3x improvement in performance by just iterating on low precision. And I really think this is a tip of the iceberg. I think we need to first really work hard on exploiting the exploiting the hardware more and more. But I think we also need to question: do we really need 64-bit everywhere? In many cases, I think the applications, need to think that through. And I'm of the belief that in many cases, it may not be needed. Certainly, the machine learning market is driving the low precision hardware, and we need to be able to figure out how to exploit that for more traditional PDE-based simulations. Say a little bit about Cocos, and then I'll move to AI. Nicholas is showing me the time here. So this is a programming model that was developed at Sandia, but has since been really widely adopted, basically an abstraction layer in C++ to really hide the challenges of doing for-all loops, doing simple arithmetic operations. So laying out data, allocating data, laying out data on GPUs. And so it is a nice model for programming portability. It ended up being and I think is a real success, and that a number of applications adopted Cocos directly. And underneath the cover, so to speak, Cocos can and is running well on multiple different hardware platforms. So this is an example of what I would call a very successful abstraction layer. And Christian Trott showed this timeline. It really was a software effort that started well before ECP in the beginning of 2016. But this is a nice timeline for Cocos, and you can see how it has continued to evolve to bring in different types of hardware and different software approaches. And so it's I think a good example of applications making good choices to adopt these abstraction layers. Again, all open source. And the ecosystem today continues to evolve. It has a lot of multiple components underneath the covers. Again, multiple different types of hardware. There are core kernels for linear solvers, or there's a core effort. And I just learned actually just a couple weeks ago. Let's see if I can keep going here. Yeah, a lot. Apologies. That there we go. Not shown here. There's a high-performance software foundation. The Linux Foundation really is working to establish a high-performance software foundation, and Cocos is going to be a part of that. And you can see how the usage of Cocos has exploded. I think it's an example of a multi-institutional, multi-year software effort that definitely has a lifetime, a very, very positive lifetime ahead of it. And so it's not just a DOE or Exascale thing. It really is a nice approach. I'll say a little bit then about I mentioned the Extreme Scales scientific software stack that really was kind of born and raised in an ECP, but actually a lot of community products were brought in that are developed outside of ECP before and after. And I think it also has a really promising lifetime moving forward. Samir Shinde, University of Oregon, has really been the brainchild behind this. It's released every 6 months. The latest release last November has a bunch of full release products. And not just the software stack that ECP invested in, but there's your typical AI software stacks as well as some of the co-design layers that I mentioned. It does have a nice business model moving forward. This is a slide from Mike Carew, where actually a commercial entity, in this case Paratools, has been contracted to do the support and work on more commercial aspects that doesn't map well at all to DOE lab staff. So this I'm very confident that E4S has a positive lifetime. Again, there's high performance software foundation. I'm not going to have time really to say much about AI. I will say a few comments, Nicholas. So I mentioned this last year that a number of us in the Department of Energy system looked at possibilities for AI for science in 2019 and then again in 22. So 2 years ago, this report was published. It's kind of a slog to read, to be honest. The first 30 pages is probably enough. But a lot has changed in the past 3 years. And, I just want to say that we're still, at least from my point of view, trying to kind of understand where we can go deep and make huge changes in science energy, apologies for the typo, and security, and where it can at least augment and accelerate existing workflows. So the deduction was really, there's kind of 4 themes where AI can and probably should make a difference in our core mission of science, energy, and security. The couple that I kind of like, I like them all, but I'll just say the surrogates, I think, has a lot of potential. I'm not going to claim that a surrogate can totally replace the fundamental simulation, but in this case can help accelerate optimization and sensitivity analysis. And, as Karen knows, there's a lot of surrogate work at her shop, and this is really hard to do. It's not like it's going to magically appear. There's some fundamental mathematics behind this. And actually using some of these AI models for like Copilot for software development, I think is really changing the game. In talking to Mike Haru, he's finding that, Cocos mods put on GitHub a few weeks ago are known by Copilot. A little scary, but in this case, I think software development can really be changed with these AI models. Just a couple more slides, Nicholas. This is an example of CosmoFlow is a analysis tool for numerical cosmology coming out of Argonne, and basically it was using TensorFlow to deduce the cosmological parameters, train on the simulation data, deduce the cosmological parameters with some level of accuracy. And it was shown that it could do pretty well with enough data. But the Livermore big artificial neural net L-band actually did much better in terms of scalability and performance. So here's an example where I think the DOE lab staff and university staff can come in and really tackle the scalability and performance challenges for training on large data sets. I'm going to cut to the chase here on a recent experience on Frontier that I find fascinating. And this is a paper here with really Prasanna Balaprakash and company. So just a couple of comments. So I'm not an AI expert. I have been reading about it, and I'm fascinated by some of the details. So in 2017, Attention is All You Need, the paper that came out that really changed the game for transformers, came out by folks at Google. And I just did a little math a while ago, but that has 108,000 citations over 7 years. That's 50 a day is what I kind of computed. And so I read through this paper. It was really hard to understand. And so I went to YouTube. My boys have taught me this, and I asked YouTube about attention, and I got a 30-minute video explaining the paper, which was fantastic. And I was thinking, where was this when I was learning numerical PDEs? And I think Rick Stevens at Argonne said, Doug, there's no YouTube when you're learning numerical PDEs. But in any case, I read this paper, and I listened to this YouTube video, and I thought, it's like they're just trying stuff. There didn't seem to be any real sort of mathematical approach. Now, I'm not denigrating it, but they literally were just trying things like mapping a word to a 512 dimension vector, and then mapping that same word to another 512 dimension vector for presence. And then attention's based on three weights. And so I thought, wow, this is fascinating, but I don't know where it came from. The point is, it worked really well, but I think there's a lot of fundamental mathematics to be had in understanding this and really continue to push the limits. That said, the attention algorithm was a game changer. And what did these folks at Oak Ridge did? They took an open source model that came out of Microsoft, Megatron Deep Speed, which essentially is an open source implementation of this paper, and really explored how can we make this puppy scream on Frontier. So really, there was kind of two things they did. It was CUDA-based code from NVIDIA, so they really found out in kind of an automated way how they could map it to the MI250X, which is different architecture. And then they exploited four dimensions of parallelism, which is what Megatron Deep Speed was kind of known for, 4 dimensions. In this case, model parallelism, pipeline, data, and sharded. So model parallelism is putting the entire, splitting up the model. Data parallelism is much easier than model parallelism. So model parallelism is splitting up the widths, okay, and that's sort of the rows, and pipeline is the layers. And so they took this code and ported it, and found that they got about 100% efficiency weak scaling and about 87% strong scaling. So very promising. Also found on 3,000. They did this on 3,000 GPUs, not on 30,000. And basically they only did sort of 10 iterations of the training. So they didn't train a trillion parameter model to convergence, which means you have kind of 20 tokens per parameter, which meant they would have needed to train on 20 trillion tokens. And in talking to Prasanna, that would have probably been an 8 or 9 month exercise on Frontier. And so I'd like to see us get that down to days or weeks. So I think there's a lot of algorithmic and software work lying ahead. The point is, I think as a community, we kind of know how to really exploit software and hardware. I think working with these large companies, whether it's Meta, OpenAI, Google, whatever, I think there's some nice collaborations ahead, and that's kind of one of the areas of focus moving forward is really trying to understand how to make these models better, higher performing, better scaling, but do it for science, energy, and security. So, a few some sides on ECP, but I should probably shut up and just take questions. Thanks for your time and attention.